So, let's begin the next topic with a hypothetical. By the way, this is an adaptation of an ancient Greek thought experiment that goes by the name of Zenos Paradox. This is an adaptation, it's a paraphrase of Zenos Paradoxes. There are, in fact, multiple of them. You could look them up on Wikipedia if you want. So, suppose I shoot an arrow at a target that is exactly 1 meter away. And suppose that the arrow travels in a straight line and hits the target. So, of course, the arrow travels exactly 1 meter. But before the arrow reaches the target, it has to travel 1/2 of the meter. So 1, which is the total distance traveled by the arrow, is certainly larger than 1/2. Well, okay, that's obvious. Now, suppose that the arrow has traveled half of the distance. Half of a meter still remains. Now, before it reaches the target, it then has to travel 1/4 of a meter. So, the total distance traveled by the arrow at this point is half a meter plus 1/4 of a meter, and this is still smaller than 1 because 1 is the distance that it will have traveled once it reaches the target. Now, at this point, 1/4 of a meter remains between the arrow and the target. But before it reaches the target, it has to travel 1/8 of a meter to get there. So, 1, the total distance traveled by the arrow, is greater than 1/2 plus 1/4 plus 1/8 of a meter. Now, 1/8 of a meter is remaining. So before it reaches the target, it has to travel 1/16 of a meter. So 1, which is the, well, okay, you can see where I'm going with this. It's obvious that you can repeat this argument indefinitely. What's interesting, though, is that the number of terms on the right-hand side over here just keeps on growing and growing and growing. But it's always going to be less than or equal to 1, because the arrow will eventually reach the target. Incidentally, I'm getting each additional term here by just halving the term that comes before it. So the general term is just n powers of 1/2. So this is interesting because it brings to mind this notion of a sum with infinitely many terms in it, which is, nonetheless, still a finite quantity. And naively, we wouldn't necessarily expect that adding up infinitely many numbers would still result in a sum which is finite. Indeed, the example above shows, though, that this is possible. If you add up infinitely many decreasing powers of 1/2, one would expect, by way of the arrow analogy, that the total sum is less than or equal to 1/2. So this begs the question, what exactly does it mean to have a sum with infinitely many summands in it? And this isn't just a philosophical question, it has practical implications. For instance, we've already seen an infinite sum being implemented in the formula for a Taylor series. So remember, that is what all of this is working towards, being able to describe a Taylor series. So here's some notation. If we try to add up all of the terms of a sequence, we get an expression of the following form. So the big sigma indicates sum. It goes from n equals 1 up to infinity. So this is exactly the same, this n equals 1 to infinity. It's the same as in the notation for the sequence. This is just whatever the starting point of the sequence is. Or if we don't care about the starting point, then we'll just write the big sigma without putting on the additional bits. This is called a series. So I want to make something clear right now. In English, the words sequence and series are synonyms of each other. The terms sequence and series are used interchangeably in English. In mathematics, they are very different. A sequence is a list of numbers, right? A sequence is a function whose domain is the natural numbers, or some set similar to that. A series is the sum of a sequence. Okay? Provided such a thing is well defined. So, speaking of definition, addition is really only defined for finitely many summands. Having a sum with infinitely many terms in it doesn't really make sense on its face. So then how are we going to define an infinite sum like this in a way which is reasonable? Well, a series is defined to be the limit of a sequence of finite sums, where every term of the sequence gets one more term of the sum added onto it. So this sequence that I am talking about is called the sequence of partial sums. So the first partial sum is just the first term of the sequence. The second partial sum is the sum of the first two terms of the sequence. The third partial sum is the sum of the first three terms of the sequence, and so on. The nth partial sum is the sum of the first n terms of the sequence. So, now we have a sequence of partial sums. And we may ask if this sequence has a limit. If it does, then we say that the series, which is the infinite sum, is equal to the limit of the sequence of partial sums. In this case, we say that the series is convergent, and this number, the limit of the partial sums, is the sum of the series. So it is the number that the infinite sum evaluates to. We are defining it as the limit of a sequence, which is perfectly well defined. If this limit does not exist, then we say that the series is divergent, or we say that it diverges. Okay, suppose that we have a series, right, an infinite sum, and we just happen to know that if we sum up the first n terms, we end up getting this formula. Well, then compute the value of the infinite sum. Well, this is just a straight up application of the definition. The infinite sum, by definition, is the limit of the sequence of partial sums. So, and because this problem was contrived to have an answer, conveniently enough for us, we have a formula for the partial sums. So what is this? Well, this is a rational function. The numerator and the denominator are both degree 1, so that means the limit is the ratio of leading terms. So, 2/3. So the value of this sum is 2/3. So, I mean, this example is kind of pointless. I mean, it's just here to illustrate the definition, but the challenge, of course, is obtaining a formula for the partial sums in the first place. Right? Like, this isn't obvious at all, that given an arbitrary series, we will be able to find a formula for its partial sums. If we can, then good. But more often than not, finding a formula like this is impossible, or at least very difficult. In this section, though, we're going to look at a number of examples where finding a formula for the partial sums is actually doable. But in general, understand that it's usually extremely difficult, if not straight up impossible, to get such a formula. Okay, so here is a super important example of a series. The following is called a geometric series. So A plus AR plus AR squared plus AR cubed. And you can represent that succinctly using this notation. Right, so when n is equal to 1, this is r to the power 0, which is just 1. When n is equal to 2, this is r to the power 1. and so on. So A is the starting term. R is the term which is getting a higher and higher power, or the factor, I should say, which is getting a higher and higher power in each term of the sum. And R is called the common ratio, because if you take any adjacent terms and divide them, well, everything is going to cancel except for this R. So R is the ratio of adjacent terms. So let's discuss the convergence or divergence of a geometric series. So this is going to be one of the very few examples where we actually can obtain a formula for the partial sums. So let's go ahead and do that. So first off, let's consider the case where R is equal to 1. Then the nth partial sum is, so the nth partial sum is what you get when you add up the first n terms of the sequence, or of the series. See, even I get them confused sometimes. Well, if R is equal to 1, then this is just A plus A plus A plus A, and so on. N times. So that's just N times A. Now clearly, NA goes to infinity as N goes to infinity. Well, it goes to either positive or negative infinity. It depends on what the sign of A is. But the point being that if R is equal to 1, then this sum diverges, because the partial sums do not have a limit. They explode. So, for R not equal to 1, let's see what happens. So the nth partial sum is going to be A plus AR plus AR squared plus ... all the way up to the nth term, and the nth term is AR to the n minus 1. Okay? Right? There are n terms here, because n minus 1 plus 1. Now, here I'm going to do something maybe a bit unexpected, but bear with me. Let's multiply both sides by R. And what do we get? Well, on the left, it's just R times S sub n. On the right, we get, well, we're going to take the R and distribute it to each individual term. So we get AR plus AR squared plus AR cubed plus ... all the way up to AR to the power n. So before that, we have another AR to the n minus 1 up to AR n. So actually, let me do this. There. Right? So multiplying by R has the effect of incrementing the exponent by 1 in every term. But now, here's where the clever thing happens. Look at what happens when we subtract these two equations. All of the terms, except for the first one and the last one, are going to cancel out. Because here's an AR, here's an AR, here's an AR, here's an AR squared, here's an AR squared. All of these terms are going to cancel out when we subtract these things. So, S sub n minus R S sub n is equal to, well, A plus AR, but AR gets canceled, plus AR squared, but that gets canceled, plus AR to the n minus 1, but that gets canceled, minus AR to the n. So something really magical has happened. where we have gone from, oops, there should be a plus here, where we have gone from a sequence of summands which may be extremely long, and we have arrived at an equation which is where we have a handle on its length, right? This guy can be, billions of terms long, and yet now we have obtained an equation which is much more tractable. In particular, we can now solve this equation for Sn, which that's what we wanted to do in the first place, right? We wanted to get some sort of formula for Sn, for the partial sums. So on the left, we can factor out Sn to get 1 minus r left over. On the right, we can factor out the a to get 1 minus r to the n, like so. And now just divide both sides by 1 minus r. So, indeed, and I'm going to put this in a box because this one is worth remembering, I think. So, geometric series are indeed one of the few examples where we can actually get a formula for the partial sums. Well, now, we want to figure out what the series is, so it remains to take this formula and then take the limit as n goes to infinity. So, the sum, which is the limit of the partial sums, oops. Well, okay, so what happens to this guy? Well, the only term that has an n in it is this term. So what's happening to r to the power n? Well, we examined this in the previous section, and we determined that r to the n goes to 0 if the absolute value is smaller than 1, and it goes to infinity otherwise. So there are two cases. Well, let me just put it like this. So if the absolute value of r is smaller than 1, this bit goes to 0. So we have just a over 1 minus r left over. And it diverges otherwise. Oh, whoops, sorry. I have to mention. There we go. So, oh, whoops, and this isn't just any generic sequence. This is that dude. So, very cool. And I put a box around it just to make that absolutely clear. So this is one of the only cases where we will actually be able to take a series and put a number to it. This is a very rare occurrence. Most of the time in the remainder of this course, when we look at a series, we're going to be asking not what it converges to, but just whether it converges at all. But here, we actually do have a formula for what it converges to, if it converges, right? If r is too big, then it'll actually diverge. Okay, so find the sum of the geometric series. So they're straight up telling us that this series is geometric, so that means that it's going to be in this form. Well, that begs the question, what is a and what is r? Because if we know a and r, then we'll be able to determine whether it converges or not, and what it converges to. So determine A and R. Well, A is the first term of the series. So A is equal to 5, the first term of the series. R is equal to the common ratio. So R is the ratio of adjacent terms. In particular, notice that R is the same as AR divided by A. So R is the second term divided by the first term. Or indeed, any adjacent terms divided. So like the fourth term divided by the third term, or whatever. So R is equal to negative 10/3 divided by 5, which is negative 2/3. Right? Because 10 divided by 5 is 2. All right. So this guy is going to converge if the absolute value of R is smaller than 1. And indeed it is. So since the absolute value of R is equal to 2/3 is smaller than 1, this series converges, and it converges to A over 1 minus R. So that is 5 over 1 minus negative 2/3. So be careful with the negative signs here. So that's 5 over 1 plus 2/3. Let's see, 1 plus 2/3 is 5/3. So reciprocating that, you get 3/5. So the 5s cancel. So we get 3. So this dude converges to 3. Interesting. So next, here's another example in the same vein. Is this series convergent or divergent? So, I mean, circumstantial evidence would suggest to us that this guy has to be geometric. And indeed, we can see that that's a reasonable assumption because the n, the index of the sum, is in the exponent. So subsequent terms are getting higher and higher powers, which is exactly the signal of a geometric series. It's when we're getting higher and higher powers. So we need to determine what A and R are. So A is the first term of the series. So how do we get the first term? Well, the starting point is n equals 1, so we plug in n equals 1. So that's going to be 2 to the 2 times 1, 3 to the 1 minus 1. So that's 3 to the 0, which is just 1. 2 squared is 4. Okay, so A is going to be 4. R is the second term divided by the first term. So that means R is equal to, well, let's see, the first term is 4. The second term is what we would get when we plug in n equals 2. So 2 times 2 is, well, let me just write it out. So 2 to the power 4 is 16. And then that's 3 to the power negative 1, so that's over 3. And then 16 divided by 4 is 4, so we get 4/3 as the common ratio. Okay, so is the absolute value of 4/3 smaller than 1? No, it is not. So this dude diverges. And that's all there is to it. Now, it's important to note that this is based on the assumption that this dude is a geometric series. But we don't actually know that. We just sort of assumed it. I mean, in this example, they straight up told us, so that's fine. But here we don't actually know. So just to be super safe, let's go through an exercise whereby we rewrite this thing to look more explicitly like this. So we can rewrite this. Oops. So we've already got the starting point as n equals 1. So that's good. So let me just mention that that is what we are doing here. So we've got the starting point at n equals 1, so that's taken care of. This is a bit of a mess, though. So 2 to the 2n. Well, that's the same as 2 to the 2 to the n, right? Because the exponents multiply. Similarly, 3 to the 1 minus n, that's the same as 3 times 3 to the minus n. So this is the same as 4 to the n times 3, and then over 3 to the n. Now, notice this is the same as 4/3 to the power n. So 3 times 4/3 all to the n. Right? Because if you have a fraction raised to a power, that's the same as taking that power, applying it to the numerator and the denominator to get 4 to the n over 3 to the n. Now this still isn't exactly the form that we want, because we want this to be an n minus 1. Okay, well, let's just take one factor and pull it out. Right? I mean, that makes sense, because this is 4/3 to the 1, to the n minus 1, the exponents add to get just n. And indeed, now we can see that these 3's cancel. So this is in exactly the form that we would expect. So a is equal to 4, as we suspected, and r is equal to 4/3, as we suspected. So we were justified in saying that this dude is a geometric series, which diverges. Okay. Now, here's an interesting application of a geometric series. When we write down a number in the decimal number system, Specifically, if we write down a decimal which does not terminate, really what we're doing is we're writing a series. So, for example, this is pi, 3.14159. So that's 3. And then when you put a 1 here, well, that's in the tenths place. So really, you're saying that you're taking 3 and then you're adding on 1/10 to it. 4, that's in the hundredths place. So you're adding on 4 hundredths. Then this other one, this is in the thousandths place, so we're adding on 1,000th. 5, well, it keeps on going like that, with greater and greater powers of 1/10. So, what we can do is we can actually show that if the digits in the decimal representation eventually have a repeating pattern, then we can show that the corresponding series is in fact a convergent geometric series. Well, if it's a convergent geometric series, then that means that we can write down the sum as a fraction. So, if you have a decimal with a repeating pattern in its digits, the fact that geometric series can be summed proves that that dude is actually a fraction. So like that's something that you might remember being told in elementary school, right? That if a decimal has a repeating pattern, then that means it's a fraction. But surely you've never proven it up until now. I mean, maybe you have, I don't know. I don't know how you would, though, without knowing about geometric series. So let's do an example of that sort of argument, where we take a repeating decimal and then turn it into a convergent geometric sum. Let's write that number as a ratio of integers. In other words, let's write it as a fraction. So, first off, so we want to write this as a geometric sum. So let us do the following. This is the same as 2 plus 3/10 plus 1/100 plus 7/1000 and so on. Now, let's take this repeating pattern and consolidate it a bit. So we've got these first two terms, but they don't really fit into the pattern, so they're just going to hang out by themselves for a bit. But these two guys, let's combine this to be a single fraction. So common denominator is 10 to the third. So to get this, you'd have to multiply the top and the bottom by 10. So 10 plus 7 is 17. Same deal here. Common denominator is 10 to the fifth. 17 on top. And you can see the new pattern forming itself. 3, 5, 7, and so on. So these guys, after these first two terms, which who cares about, these guys form a convergent geometric series, is my claim. So let's see. If it's a geometric series, well then what are A and what are R? Well, A is the first term of the series, so that means A is going to be this. Again, we're ignoring the first two terms because that's outside of our pattern. And R is equal to the ratio of the second and third terms. So that is or I'm sorry, the second and first terms, like so. And we can simplify this. because this is the same as right? Dividing fractions is the same as multiplying by reciprocals. So this is the same as 1 over 100. So this number is 1 plus 3/10 plus, and then a convergent geometric sum. So a over 1 minus r. So, I mean, does this guy even sum? Well, certainly. R is 1/100th, which is smaller than 1. So we get a 17 over 10 cubed over 1 minus r, which is 1 over 10 squared. And let me do it like this. Okay, so indeed, this is a fraction. Now all we need to do is just simplify this. Oh boy. So let's see. Common denominator of the first two guys is 10. So we get 20 plus 3, so 23. Now, as for this dude, I'm going to multiply the top and the bottom by 10 squared. Well, actually, no. I want to get rid of this 10 cubed, because having a fraction on top of a fraction is making me nervous. So I'm going to multiply the top and the bottom by 10 cubed. So that cancels out the 10 cubed here, and on the bottom it distributes. So 10 cubed over 10 squared is just 10. Okay. So so 1000 minus 10 is 990. Does that make sense? Yeah. That's good. Does that make sense? Hang on. Yeah, we're good. I'm sorry, just double checking. Okay, so what do we get now? Well, what's the common denominator here? I mean, the common denominator is going to be 990, because 990 is a multiple of 10. So specifically, I would have to multiply by 99. So 23 times 99 plus 17, like so. So finally, we get, let's see. So on the top, we get 2294. And then I believe that we can reduce this. Yeah, these are both even numbers, so we can certainly pull a 2 out. So if we divide the top and the bottom by 2, we get 1147 over 495, and I think that's the best that we can do. I think it's fully reduced at that point. Okay, cool. So that is what this repeating decimal is as a fraction, 1147 over 495. And we used calculus 2 to do it. So we used calculus 2 to prove a fact from elementary school. I think that's kind of neat that, these things were sort of hiding in the background of our math knowledge all this time, and we just never really thought to ask until now. Okay, so that's a neat application of geometric series. Now down here, we have an example of what's called a telescoping series. So here's another example of a series where we will actually be able to explicitly find a formula for the partial sums. And the idea is to take the general term and expand it using partial fractions. And then once we do that, we will be able to see that most of the terms actually cancel. And in that way, we'll be able to find a formula for the partial sums. Okay, so let's take this dude and expand it in partial fractions. So let's see. So we have the case where the denominator is distinct linear factors. So that means we're going to get one partial fraction for each factor, like so. Now let's clear the fractions. Multiply both sides by n times n plus 1. Here the n cancels, but the n plus 1 does not. Here the n plus 1 cancels, but the n does not. Now to figure out a and b, let's pick a value of n which cancels the two terms. So to cancel out this one, let's let n equals 0. Then we get 1 equals 0 plus 1. So that's just a times 1, and that goes away. So cool, there's a. To get n plus 1 to go to 0, let's let n equal negative 1. Then we get 1 equals 0 minus b. And so b is equal to negative 1. So plug in the partial fraction decomposition into the sum. Right, so a is equal to 1, b was equal to negative 1. And we get that. And let me just put big parentheses around it to indicate that this whole thing is part of the argument of the sum. Okay, so now I claim that we will be able to write out a formula for the partial sums. So let's write out the first few partial sums and see what happens. Hopefully we will be able to observe a pattern. So let's see. S sub 1, the first partial sum, is what we get when we plug in the starting point, so n equals 1. So that's just going to be 1 minus 1 half. Next, S sub 2. So S sub 2 is going to be the first term plus the second term. So that is 1 minus 1 half, that's what we already have, plus the second term. So if we plug in n equals 2, we get 1 half minus and then 1/3. So notice now, this minus 1 half plus 1 half, that cancels. So really, we get 1 minus 1/3. Okay. The next partial sum, well, that's going to be everything that came up to this point. So 1 minus 1/3. And now we're going to add on the third term. So that is 1/3 minus 1/4. And hey, wouldn't you know it, this minus 1/3 and plus 1/3 cancel each other again. So we appear to be seeing a pattern. Every additional term that we add on just cancels out with one of the terms that we had before. So 1 minus 1 over 2, 1 minus 1 over 3, 1 minus 1 over 4. Let's do one more. So S4, so that's everything that we've gotten up to this point, plus the fourth term of the series. So these 1/4 cancel. Like so. So I think we can see the pattern now. It's 1 minus 1 over whatever the index of the partial sum is plus 1. So S sub n is equal to 1 minus 1 over, right? Here we had a 5, this is a 4. Here's a 4, this is a 3. So it's whatever the index of the partial sum is plus 1. So, to figure out what the sum is, all we need to do is take the limit as n goes to infinity of the partial sums, which, clearly, as n goes to infinity, this dude here is just going to go to 0. So we get that our sum is the limit of the partial sums this dude down here is 1 over infinity, which goes to 0. So our final answer is 1. So this dude is 1. So that's an example of a telescoping series. So we have 2 series so far that we've looked at where we're actually able to get formulas for the partial sums. Geometric series, we can do it, and telescoping series, we can do it. So here's an example which is worth memorizing. The harmonic series is the sum of reciprocals. So 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. So it seems counterintuitive, but as it happens, this sum is actually divergent. So I don't really want to go over the proof, but feel free to look at this if you want. The point is, if you add on enough terms, you will eventually add on a chunk which is larger than 1/2. So if you go far enough out in the series, you're going to add on a bunch of terms which exceed 1/2. And so, if you go out far enough, you'll find that you're getting 1 plus and then a whole bunch of 1/2s. Well, clearly, as n goes to infinity, this dude is going to explode, so that means that the partial sums are themselves going to explode. So yeah, look through this if you want, but really I just want you to remember that this dude here diverges. And it's not immediately obvious, I think, that would be the case. Okay, so here's a fact. If a series is convergent, then it must be the case that the terms, the individual terms of the series, are tending towards 0. Okay? If a series is convergent, then the terms of the series must be tending towards 0. I mean, imagine if they weren't. Imagine if the terms of the series limited themselves at like 3, for instance. Well, then that means that in this sum, you're just adding up infinitely many 3s, which is going to explode. So indeed, these guys have to be shrinking to 0, otherwise there's no chance of the sum existing. The opposite of this, however, isn't true. Just because the terms of the series go to 0, that doesn't necessarily mean that the series converges. Indeed, we just saw an example of that. 1 over n clearly goes to 0, but the sum of 1 over n explodes. It does not converge. So I don't want to see you making that mistake, where you just say, oh, well, the terms of the series are going to 0, so the series converges. That is absolutely not the case. There's a lot more that goes into the question of whether a series is convergent or not. Yeah, so here's the other example of a divergent series we had. This is sort of a bad example because here we have 4/3 to a power, Well, indeed, in the limit as n goes to infinity, the terms of this series are going to explode. So that is not an example that we're looking at. Okay, so as a consequence of this fact, we have the following test for divergence of a series. If the limit of the terms of the series does not exist, or if this limit is anything other than 0, then that means this series must diverge. That's basically just taking this statement and taking the contrapositive of that. So if A, then B, the contrapositive is if not B, then not A. So if the limit is not 0, or doesn't exist, then the sum is not convergent, right? That's the contrapositive of this statement. And that's the divergence test. So that's an easy way of just glancing at a series and being able to tell whether that if that series diverges. Because if you can glance at a series and say that the terms of the sum are not going to 0, then you're done. It diverges. There's nothing else to say. So for example, show that this dude diverges. Well, look at the limit of the terms. Right? If we look at the limit of these dudes, what's going on here? Well, well, we've got a rational function. The polynomial on top has degree 2. The polynomial on the bottom has degree 2. It's the same degree, so that means the limit is the ratio of the leading coefficients. So 1 over 5. Well, this sure isn't 0. So this is telling us that eventually this sum is just going to be adding up millions and millions of 1/5s, which, yeah, of course that's going to explode. So by the divergence test, we conclude that this dude diverges. Yep, because the limit of its terms is not 0. So finally, before we wrap up this section, we just note a couple properties of sums. So if the sum of this, so if these two series both converge, if these two guys are guaranteed to exist, then multiply the terms of the series by a constant. Well, you can pull that constant out. Add up the two series, and you know the sum of the sum is equal to the sum of the, oh, that's awful. Whatever. The sigma distributes over the sum. The sum of the sum is equal to the sum of the sums. That's what I wanted to say, but that's terrible. Whatever, you can look at it. The sigma distributes. This is reliant, of course, on these guys even existing in the first place, though. So, for example, find this sum. Well, this is this situation right here. So what we want to do is we want to see if the series with terms here and terms here both exist. And if they both exist, then fine, just take their sum. But they have to exist in the first place. Well, yeah. So first, let's look at this one. Well, we've already looked at this, in a sense. We looked at 1 over n times n plus 1. And here we have 3 over n times n plus 1. So we already know that this dude converges. So since 3 is a constant, we can just pull it out front. That's what this first property is telling us. And this sum ended up being 1, so this is just 3 times 1. By the result of example, which one was it? 6. So what about the other constituent, sum? Oh, well, this is the Zenos Paradox, sum. This is the one we were looking at the very beginning, where we were adding up 1/2, then 1/4, then 1/8, then 1/16, and so on. So sure hope that this guy sums, otherwise Zenos Paradox isn't really a paradox at all. Well, actually, no, then it's a super paradox. That would make even less sense if this guy diverges. Well, anyway, this is a geometric series. How can we tell it's geometric? Well, because this is the same as 1/2 all to the power n. Right? So, if we want to take advantage of the fact that it's geometric, we need to write it in this form, ar to the n minus 1. So the starting point is n equals 1, so that's fine. So let's just pull out a factor of 1/2 so that we can get that n minus 1 in the exponent. So this is a geometric series with a equals 1/2 and, right? So a equals 1/2 and r also equals 1/2. Right? R is the bit that's being raised to n minus 1. So R indeed has its absolute value less than 1. So this guy converges. So it converges to a over 1 minus r. So that's 1/2 over 1 minus 1/2. 1 minus 1/2 is 1/2. 1/2 over 1/2 is 1. So cool. The arrow does, in fact, travel 1 meter, as we would expect it to. So the two constituent series both converge, so that means we can take this sum and distribute it. So this was 3, and this was 1. Okay, so our final answer is that the whole thing sums to 4. Okay, so that's it for this one. I would suggest that of the ones that we looked at here, telescoping series is neat. You might see an example of that in the homework or something, but really what's important is to memorize this. You should memorize this fact about geometric series right now. This is maybe the core of this section going forward. Also, the divergence test. This is also important to remember, as this is going to be coming back. Okay, see you next time.